So if we have these two formulations here, right, let us first and foremost proceed to find their respective modulus and arguments. In the case of R1, we would have the square root of 2 squared plus 3 squared, which would give us the square root of 4 plus 9, right? Which of course implies that R1 would be equal to the square root of 13. And then on the other side, for R2, we'll have the square root of 1 squared plus 4 squared, which would be the square root of 1 plus 16, which in fact would be that R2 would be the square root of 17. Now from here, if we now take some few identities, we can take that theta 1 would be tan inverse of 3 over 2, and then would have theta 2 to be the tan inverse of 4 over 1, which is the same thing as saying the tan inverse of 4. Now that we have gotten the values of the modulus and the argument, let us now find some values using this example to showcase exactly what we're talking about. In this case, let us first start with z1 squared. That is, multiply z1 by itself. Now, in one of our previous classes, we have talked about how to carry out algebraic multiplication. So in this case, it will be 2 plus 3i multiplied by 2 plus 3i. You can go over that previous video so that you see exactly how the process is done and also apply it to this concept. But in this video, we will be utilizing the De Moivre's method to doing this, which is by using the polar representation. Now, in this case, we would have R1 squared into cos 2 theta 1 plus I sine 2 theta 1, right? Just replacing n by 2 because we are taking the square. Now, it follows that z1 squared would now be equal to the root of 13 all squared into cos 2 multiplied by 0.31 squared plus I sine 2 multiplied by 0.31 squared. This would be our representation. Now, do not forget that we can still further simplify this as cos 0.62 pi plus I sine 0.62 pi. So simplifying those values further, we would have that z1 squared will be equal to, as far as this is concerned, minus 4.79 plus 12.09i. This would be the representation of this back to algebraic form. Now, I should also note this, that there is bound to be some approximation error that will arise in this conversion from polar form back to its algebraic form. And the reason for this approximation error arises from, number one, when we found this argument of the complex number, you realize that we had to convert it to radian. First and foremost, the angle in itself was not a special angle, which means that it would have a ton of decimal points. Now, those decimal points have been approximated, which gives you the first approximation error. Then when converting to the radian, it is approximated again, which gives you another approximation error. Now, when converting from the polar form back to the algebraic representation, we had to approximate yet again. So this would lead to some approximation error, which would make the value slightly different from the exact value. The exact value would be what you obtain when you take the algebraic multiplication of this. So by using the concept we learned in the previous videos, carry out the algebraic multiplication here to find the exact value, and then compare that exact value to this value to see just how much approximation error is placed there. Now, we can also carry out z1 multiplied by z2, which nominally by the algebraic method would simply just have been 2 plus 3i multiplied by 1 plus 4i. But in this case, we are, just as I've said, carrying out the Moivre's method in this case. So here we'll be utilizing R1, R2 into cos theta 1 plus theta 2, then plus I sine theta 1 plus theta 2. So in this case, what would we have? We would have root 13 multiplied by root 17, and then all into cos 0.31 pi plus 0.42 pi. Then we have plus I sine 0.31 pi plus 0.42 pi. So if we were to continue simplifying this, we would have the square root of 221 into cos 0.73 pi plus I sine 0.73 pi. Now that we have this, we can, just as we have always done, take this and find the representations of this multiplication. So now we have gotten the final result, right, after converting to the algebraic form, minus 9.83 plus 11.15i. Now, just as we said earlier, there would be some approximation errors that would be occurring here because of approximations to the argument, as well as the approximations when converting back here from their various decimal points. So from here, of course, you can also take the division and see what the value would be like, or take more power representations in the power of 3, power of 4, power of 5, and then try as much as possible to compare if possible. The reason why the Moivre's theorem is so important is because of the fact that when you get to higher powers, you no longer would find it convenient to carry out algebraic expansions. For instance, if we were taking z1 raised to the power of 5, the algebraic expansion would be very, very long. However, with this same number of lines, we would be able to find z1 raised to the power of 5. That is just how seamless the De Moivre's theorem is. Now that we have looked at how to carry out power multiplications as well as multiplications and divisions of complex numbers, in our next video, we would exclusively discuss how to find the roots of a complex number. Or you can also say we are looking at fractional powers of a complex number, the square root, the cube root, the fourth root, and so on and so forth. This will be our focus in our next video. As always, please like, share, and subscribe to the channel, as well as turn on your post notification so that you'll be alerted when new uploads are made. Thank you.